I noticed part of the the goal of the talk is to provide a framework for understanding the definition of virtual double category double category. The talk is titled Algebraic Patterns of Segal Conditions. And David Jazz was actually the first person I probably heard the word virtual double category from, but at least seriously thought about it. And it was this time David Jazz began this work on double categorical systems theory during the pandemic. And in sort of late summer 2020, I flew back to Boston to move here to the West Coast. And we went on this lovely walk along the Charles River, up through into Mount Auburn Cemetery with the sort of light filtering through the leaves in the late summer, early fall. And my wish for this talk is it's just like that walk.
Beautiful. Thank you, Brendan. That's wonderful. I don't know if I can actually live up to that. It's going to be there's going to be a little less light filtering through the leaves on this talk, but this is going to be a talk about a mathematical gadget that I've gotten interested in over the past couple years that I keep talking about to people at Topos. And then they keep saying, "Oh my God, that sounds like a big headache. Like, I don't want to think about things in that way." And so I've been saying, no. It's so nice. It's so clean and so conceptual. And no one will believe me until I actually tell them the clean conceptual point of view. So that's going to be this talk. So it's going to be a talk about these things called algebraic patterns, which are this concept due to Chu and Haugseng. The paper that they wrote is called Homotopy Coherent Algebra via Segal Conditions, and that makes it sound way scarier than it actually is. In fact, I'm barely going to even do anything with algebraic patterns in this in this talk, because I've decided sort of at the last minute to just give you my own homebrew formulation called the double pattern, which is more in line with a lot of things we do in Topos theory, a lot of Evans double theories, for example. And that's going to give us a definition of virtual double category that generalizes immediately to a variety of other categorical algebras. So, okay, so the first thing I want to do is explain what Segal conditions are. And I'm going to do this in the ordinary setting of ordinary categories. But the basic idea is that when I talk about categorical algebra, if I close the window, I'll fall asleep. So I'm sorry about that. By categorical algebra, I mean doing things with categories that have extra structure or things that are like categories. So things like categories, monoidal categories, multi-categories, operads, props, and various other structures like that, polycategories. These are all varieties of categorical algebra, and this is going to be an approach to describing those. So there's 3 ways to describe categorical algebra, 3 ways to do. This is not nearly exhaustive. Categorical algebra. By the way, by categorical algebra, I mean sort of algebra on categories rather than algebra in categories, although the 2 perspectives are useful for each other. So one will be what I'm going to call essentially algebraic theories. Essentially / generalized algebraic theories. And these are basically like we write down the objects, so e.g. a category. A category is a set of objects, C naught, for any 2 objects, a set of morphisms, CAB, and this here is our underlying structure here, C. Then so this is some sorts. And then we have some operations. So a function, I'll do semicolon, CAB times CBC to CC, and another operation id, which is it's a nullary operation or a single element of CAA, and then some rules. So these are operations. And then we have laws. So So these things should be familiar. This is a sort of familiar definition of a category, and we can do this kind of definition for all sorts of categorical algebra, things like props, things like multi-categories, things like, you know, other kinds of things, symmetric monodal categories. But there's an issue with this kind of thing, which is that it becomes quite unwieldy when we're using a more complicated kind of categorical algebra to describe things in this way and do things in this way. It's easy to check that you have one because we've listed out sort of very minimal kind of conditions for it. That is, it's easy to check if you have one if all you know about it are that you have objects, morphisms, and then these operations, and then you want to check. Sometimes it's a less is less in category theory. So we'll be doing a more is more approach through the rest of this talk. But the problem here is like, so one nice thing here is you have this sort of underlying graph here. And this is sort of the non-algebraic structure which lives under a category, right? And then you have on this operations and laws. But the thing is, if you have more complicated operations, you always have to pass through the fact that you have these like associativity laws. It's not a big problem with categories, and a lot of what I'm doing is it's severe overkill because I'm going to give you the example of categories. But even with monoidal categories, we have an issue with writing things like this because we start to have all these things where we want to write expressions like f then g, or like, you know, f then g, and then we have like h, sorry, f tensor g, and then we have h tensor id, and things like this. And when these become more complicated, it becomes hard to even understand what we're really doing when we do these things. So we have a solution for that, which is we have string diagrams, or pasting diagrams. By three ways. They're going to be split into 1, 2a, and 2b. Thank you. I like to be consistent here. So 2a. So what are string diagrams? Well, this expression here for a symmetric monodal category could be written instead like this, right? I could say, like, for example, I have this thing here. I could write this string diagram and this is a perfectly good, in a strict monodal category, or a prop, let's say, a perfectly good description of this composition. And boy, isn't it nice to look at that, right? Now, so this is something that we've been doing for a while, since, I guess, Segal and Street's paper on doing string diagrams for symmetric monodal categories. And we use this for a lot of different things. For example, David and Brendan came up with a way to do some really rather Baroque, essentially algebraic theory of things called hypergraph categories as algebras for an operad of certain undirected wiring diagrams. So how does this work? Well, in the operatic point of view, we have this string diagram thing. And so I'll write that up again because I probably should have just drawn it over here. Oh. Here's my string diagram. And now I'm going to label these things with objects. And then I see this as a morphism from the inner boxes. I see this as a morphism from the inner boxes to the outer box. And these compose by nesting. So I could, for example, factor this through a binary one if I, for example, put these two in a single box before, right? And if I maybe put these in a box, this is all factoring in the operad. And when I put these in a box, finally, that way of nesting corresponds to this algebraic expression. So we haven't lost anything in terms of expressing the algebra, the underlying algebra, but we've gained something, which is that we now can express unbiased multi-array compositions that are structured according to the nature of the algebra without having to write them down in a planar and Baroque kind of way that is based on our sort of more basic operations. So this is nice, but there's something we're missing here, which is, I should say what a category is. So a category is an algebra for this operad. And it's a category, the diagrams here actually had to have wires labeled already with objects, so it's a category with that set of objects.
You mean a monoidal category is one?
Yes, sorry. Technically it's a prop. Well, yeah, I didn't say exactly what this is, but yeah, an symmetric monoidal category with that, for that operad with that set of objects.
And you can get category right if you insist on only like unary boxes.
Yes, in fact, I should, I wanted to do this because it was a string diagram and I wanted to show the reason we want to use string diagrams, but then I'm going to go right back to my simple example of categories, which is what I'm going to do the rest of the time. But again, these methods are overkill for categories. The point is to do them for more complicated things. I'm just giving you the, I'm out of coffee. The point is to give you the example. So for categories, right?
That's an emergency.
Right. So for categories, it would be more like, I'll just write it in here. And for categories, it would be more like this. So what is an algebra? It's like you fill the boxes. Each has one now. And then this is just one big box, just to give you string diagrams for categories, because we're going to see them a lot. A, B, B, C, C, D, A, D, A, D. Okay, here's a string diagram from a category. Again, overkill for categories, but the idea is that this generalizes. And now, what is an algebra for this operad? So we see the operation, we see the possible compositions as morphisms in this operad, and we see the act of filling a box as sort of a functor of operads into set. I'm not going to go, this is not important for the thing, so if you don't know what this means, it's okay. This is just to sort of set, for people who do know what it means, this is just to set the stage. We're not going to do this, right? The whole point about this that's missing is, first of all, we had to pick the set of objects right away, and second of all, what's missing here is that when I look at this diagram, right, I can see various features of it, which is that it's built out of other diagrams, right? It has subdiagrams. I can look into its parts. And it's not very clear in the operad what corresponds to a subdiagram. Now, you can write it down, you can figure out different ways, but it's just not like part of the actual structure. So in here, we really didn't have any, in here we didn't write down this notion of like unbiased composition pattern, right? Or what is known in higher category theory as a pasting diagram, which is the term I'll use generally. And then so we move to operads, and now we have this notion of pasting diagram or unbiased general composition. But now we don't look at the combinatorics of that diagram. We can't see into it, and we therefore can't manipulate it as we can't, like mathematically, the way we can when we're actually drawing it. Sophie?
By unbiased, you mean like you didn't have to write, did you do F composed G and then H, or F and then G composed H? In a pasting diagram, you just have all three, because of course they are supposed to be equal.
It's exactly right. So what I mean by unbiased is this is biased as it's biased towards binary composition, but you can derive n-ary composition, or in this case, ternary composition, composing three things, right? But I have to actually write it down using this definition, I have to pick which way to associate it. So I have to bias my writing to a certain way, but they're equal. Okay. In this way, I can just say compose all three of them, but I can recover the other two by factoring this through other things. So I could do that, or I could draw the box around the other two. Okay, so the final thing here is we can use an algebraic pattern which will allow us to actually have, it will be a category. So a category whose objects are pasting diagrams. Or I'm not saying string diagrams because they're not always going to be made of strings, right? But pasting diagram is sort of I think the appropriate term here. whose objects are pasting or string diagrams, and the morphisms come in two kinds. So two kinds of morphisms. One are known as inerts. And this is where I'm going to start to color code everything. Inerts will be pink, and they are subdiagrams. Inclusions, subdiagram inclusions. And then two are so-called actives. And those will be written in blue. And they are actual compositions. So they will they will be maps that tell us how to compose things somehow. And we'll see what this looks like in actual diagrams in a second. So we will build an algebraic pattern, which is some category with some stuff and more things that I will add on. Out of the theory of categories like this. We note that these diagrams here, the inside part, they actually correspond to some very special categories, right? So we'll note that we have categories. This diagram freely generates a category. In graph notation, it's this category. Again, this is not the whole category, right? Because the whole category actually has some more stuff. It has the composites. So that's the whole category, right? So, or maybe I'll draw it in a better way. 1 second. Here are my three things, but then I can draw the backwards, that one, that one. There's my category. If this is A, B, C, then there's A, B, and C down there, the rest of the composites. Okay, so that category is freely generated by that diagram. From any one of these diagrams, which are strings of beads like this, I can form a category like that. And that gives me a full subcategory, so like full subcat of cat on the pasting diagrams. These are called the pasting diagrams. Is delta by definition. That's also known as the simplex category. If you're a homotopy theorist, this is a simplex. Yes.
Wait. Aren't A, B, and C the strings, not the boxes? Or
Yeah. Sorry. Let me. Yeah. F, G, and H. Really, it should be like 1, 2, and 3. Like they're not like semantic things. This is like me looking at the picture. The first one, the second one, the third one. Okay. So we get a full subcategory of categories on the pasting diagrams, delta. So what are the maps between these? They're functors, right? They don't look at the, so my example here of an algebraic pattern will be delta in cat, which is full on the string, the composable sequences, says, aka pasting diagrams. I'm saying it in this general way because this is how you do it. You know, if you're doing symmetric monodal categories, you're going to take the symmetric monodal diagrams, you're going to generate free symmetric monodal categories out of them, and you're going to use a full subcategory of symmetric monodal categories on that. Right? Okay. So the two kinds of morphism here, inerts, they're going to be functors that are induced by induced by maps of graphs. So they're sometimes called free. Just as these are free on graphs. The graph here is these three things, freely generated on that graph. And if the functor comes from that, then it will be an inert. And let's look at an example of that. It's going to go over here because I'm going to need this diagram again. And I'm going to look at my notes so I don't mess this up. So as an example of that, here's 2-ary composite. Here's 3-ary composite. And then my pink inert here is going to go in between. And what I'm going to do is it has to be free on the underlying graph. So what does that mean? Right? Well, it means that I can't send any of these basic squares, who are the basic arrows, to any composites. They have to go to an individual square. So it turns out that that's a subdiagram inclusion. It is an injective map, which is distance preserving, is one way to say it. OK, so here, this is how I'm going to draw them. As you can see here, this maps into there, and I'm going to pick out this subdiagram. So this is the special thing about algebraic patterns. We now have this notion of subdiagram. But then there's another thing we have. Yeah?
How do you formalize this distance preserving property?
So you can see these categories as being, if I write this as being 0, 1, 2, 3, right? Then an arrow, one of the primitive arrows, goes between n and n plus 1. And by distance preserving, I mean preserves distance in that it does not send an arrow to something that is longer. The composite arrows are longer.
You also just said it's a map of graphs.
It's a map of graphs is the more correct way to think about it, right? So this is a graph. The graph itself is this, right?
Oh, and not the composites.
Not the composites. The free category generated by that graph has more arrows, the composites. Even though we often write it like this, we often write down this, but we're implicitly using the fact that there are composites. But I'm saying I actually want the maps that come from the graph. And because that's what distance preserving means, the composites sort of get longer when you write them. So, yeah.
Doesn't that privileges some of the arrows over others?
Yes, it does. These are the inert arrows. They correspond to subdiagram inclusions. So I'm marking out a special concept. Some arrows are inert. Yeah.
The inerts are a subclass of the actives.
No. The inerts and actives, as we'll see, but not yet, form a factorization system. They are literally orthogonal. And I'm going to draw them that way. That's actually my main novel contribution to this is to draw the inerts and actives orthogonally on the page. OK. So actives are sort of, in a sense, opposite. They are going to be boundary preserving. What does that mean here? It means it's a functor that preserves the boundary of the diagram. What is the boundary of the diagram? It's what would stick out at the edges if you boxed up the whole diagram. So in this case, it's just the first object and the last object. So if you have any map that preserves the first object and the last object, that's called active. Now note, an active inert must be an identity, or an isomorphism in this case, right? Because if I was given by a free map on graphs, and I sent the first one to the first one and the last one to the last one, then I have to just map exactly on. Let me draw you an example of an active. Here we go. So an active is going to be done in blue here. And now an active, diagrammatically, is a swallowing morphism. The boxes here swallow up boxes here. So let me draw that. So in blue, I'm going to make this a little better. In blue, I will draw, you'll note that I'm going to be drawing the, sorry, I'll write this. I'm going to write it like this, but OK. An active, in blue, I'm drawing this thing, OK? And in black, I'm going to draw this thing inside it. I'm going to draw the codomain inside it, like this. So you see that the boxes of the blue swallow the subdiagrams of this thing. That's an active. And how does that correspond to a composition? Well, look at it. That tells us ways that we can compose all these subdiagrams to fit into these boxes. In particular, there are some extra special things. So this is active. They're boundary preserving maps. Okay, and then we can add a few other things. I am getting confused with my pens here. How does it? Oh boy. Oh boy. 3, we have some set. Well, let me call it a full subcategory. Category P for pastings. Full subcap PL of P inert. So we have a full subcategory of the inerts. By the way, that's just meaning I picked some objects that are special, and these are called elementaries. And here we have the elementaries are the wire and the single box. These diagrams are not built out of any other diagrams. This is a sort of a free parameter in our theory. We get to say what is elementary. Sophie, you had a question?
Yeah, I feel like I'm following almost everything, and yet I'm like, I don't understand what delta inclusion cat is doing.
Delta inclusion, delta is my example algebraic pattern. It is defined to be the full subcategory of categories on the pasting diagrams.
Delta is the full subcategory of the pasting diagram.
Of cat. Spanned by the pasting diagrams, which are the free categories on the paths.
How is that related to you have a category P?
So this is my abstract definition. This is my running example.
Delta is an example.
P, yeah, delta is an example of P.
Okay.
Yeah, is one such P. And then in like we have part of the data of this is that we have these two classes of maps and this extra bit of data here. So this is all data, and then I'm going to add law.
Sorry, can you be real dumb for sorry, this is not dumb, but like what? Can you give me an example of an object in delta?
An object in delta is like, for example, here's a graph.
That's an object in delta.
We generate the free category on it. That's an object of delta. Another way to say delta is it's the category of finite non-empty ordinals. Okay? Totally ordered finite sets and order preserving maps, which is the same. Another way to say is that its objects are the natural numbers, and its morphisms are functors between paths of that length.
Cool.
Yeah.
I like that one.
Oh, yeah, okay.
Yeah. So, right, but the way I'm describing it as the full subcategory of your algebra, the models of your algebra on the pasting diagrams is always going to work. So that's why I'm saying it that way. Okay, so then we have this full subcategory of elementaries. They'll come back later, but we won't. I'm putting them here just so that all the data can go in a row, but I'll explain those later. Because we'll need these to define what a category, to recover the notion of category out of the algebraic pattern, quote unquote, for categories. So the fourth condition is that actives and inerts, so active comma inert, is an orthogonal factorization system. So what does that mean? I'm not going to tell you what an orthogonal factorization system is. If you know, you know. But what it means is this. I can factor any two of them that are in the wrong order. So note that I said active inert is an orthogonal factorization, not inert active. If I have a composite of the form inert active, I have to be able to factor the composite, like this implicit diagonal here, into actually an active followed by an inert. Okay? How do I do that? Well, let's look at this. Remember that inerts are subdiagrams, and actives are these swallowing things here. So what I want to do here is I want to figure out some diagram to put up here, which is a subdiagram of this, and where I have a swallowing of this into there so that the square commutes. So what could that be? There's only one answer here that I could possibly do. This is a subdiagram of this. Now this tells me how to compose things into here, which says each of these boxes is filled by a subdiagram here. So I can just look at the subdiagram of these left two things, look at over here what gets swallowed by those two things, draw that up here. So this one swallows these two, and this one swallows this middle one. So I only need 3 up here. And then that gives me right away this subdiagram here, which is an inert, and then it also, I'm out of blue, gives me this swallowing here. Sorry?
Swallowing is biased.
It's still unbiased.
How is swallowing unbiased? Because you have to pick, you have to like make some choice about like.
What to swallow?
Yeah.
Well, this is like a, it's they're all of these actives, right?
Yeah.
Are given by are like expressing different kind of compositions you can do.
Right.
So it's all the different kinds of compositions you can do. So it is, in sense, all the biasing. So it's like, as a whole, it's unbiased. Oh, wow. Kevin, you filled my coffee. Thank you.
Are the unswallowings also active?
What are those?
Like, is there a corresponding blue arrow the other way for the, like, unswallowing?
No, you can't. There is no map that way. So maybe it's worth thinking about what this is as a functor. Remember that the wires are the objects and the boxes are the morphisms. So what does this functor do? It sends this arrow here to the composite of these two arrows. That's why you can't go the other way. Because if you wanted to go the other way, you'd have to send this arrow to what? Maybe this one? And then, like, it's not, you can maybe define a map like that, but it's not going to be either active or inert. Like general functors in here are composites of actives and inerts. That's what being a factorization system means. Every map is expressible as an active followed by an inert. But I'm not going to, I think this definition, well, really, really great and really cool, is not going to be the one, this is not the one I'm going to talk about as I, am I halfway through 35? And I ended huh?
You have about 25.
All right. So as I start to ramp up this in the usual way, we're gonna leave this behind. But I need to tell you, we need to actually get categories out of this. So hopefully in 10 minutes I can tell you how to do that, and then we'll have a really fun 15 minutes at the end. So right. Oh yeah, 4. Trust me. I mean, I just sort of showed you how you do it, but that's how it works. If you're cool and you can read Australian category theory and you've read Lawvere, this is the generic free factorization system associated to the classic category of a familial monad, and that is they're highly related to algebraic patterns. Not going to go into that. To the free category monad on graphs. Yeah. So in general, like there's a condition on algebraic patterns called extendability that makes them correspond to familial monads. So extendable algebraic patterns correspond to familial monads. So not going to go into that. But OK, cool. So now let's notice something. So define the nerve. So now we're going to do nerves. The nerve functor. The nerve of this functor, OK, is this functor. So n is defined to be the following composite. We go from cat to Presheaves on cat using Yoneda. And then we restrict along the inclusion I to go to Presheaves on delta. So what does this do? It sends a category C to all the way here, but I'll draw it over here, to the functor cat I dash C. So let's work out over there what this really means, right? First of all, remember that the objects of this correspond to the natural numbers, so I'm going to write them out like that. But we'll do this. So this is the nerve. So the nerve of C, and then we'll take it at the wire, which is an object, right? That is going to be, by definition, that's cat from the wire to C. And we'll note that that is the same thing as, that is bijective with the objects of C. Right? A functor from an object to from this category with just an object to that category is an object. Next, we do the box. Our formula says it's a functor from one arrow category with two objects and one arrow between them and some identities. A functor out of there just tells me where that arrow goes. So this is equal to C1, the set of objects. This is the set of arrows. All right? So I will note right away that living within this nerve is the underlying graph of the category. Specifically, these two special objects that I just looked at are the elementaries, which are part of the data of the algebraic pattern. So if I restrict it to the elementaries, I get the underlying graph. And in particular, you always want to think of the category of elementaries as only consisting of the inert morphisms. So this is the underlying non-reflexive graph. Just don't worry about that if that was too much, but here we go. Now let's look at the cool stuff. What happens if we do it on anything else? Well, again, it's cat from this category to C by definition. Now what is that? Well, a functor out of there, right? There are three morphisms in this. There's the left one, the right one, and the composite. So this is actually a commutative triangle, which, by the way, is why this notation is triangle here, because it's a category of generalized triangles. It's a commutative triangle in C. Okay? So now, there's something really special about categories, which is that commutative triangles, right? So f, g, and h, such that h equals g of f, are uniquely determined by the two things in the back. So let me write that out. NC of two boxes, we can restrict to this thing, NC of one box pulled back over NC of the wire, NC of the other box. That pullback, yeah.
I don't really get why NC of the two boxes is the commutative triangle.
So this category here is a free category generated by the two-length path. Right? So it has three arrows, three non-identity arrows. The first one, the second one, and the composite.
Yep.
And the composite equals the composite of the first two arrows. A functor out of that must send each one of those arrows to an arrow. So it picks out three arrows. Also the identities, but the functor has to send those to identities. And it has to preserve composition. So it must send the composite to the composite of the first two you pick. Hence, commutative triangle. Now, we can restrict, what is this? This is the set of, this here is the set of arrows like this. This is the set of commutative triangles like this. And this is the restriction, by which I mean like you just take the top two. Now this is an isomorphism. I'm putting it in red because it's so important. It's an isomorphism. Bang. And that is the Segal condition. We'll come back to that a little more, but I'm going to put the Segal condition in huge letters because this is sort of one of the titles of the talk. Wow, that's where it's from. So this is an isomorphism. What does that say? Well, that says this. A map is an isomorphism if for every element here, there's a unique inverse image, right? In other words, for any two pairs of arrows that line up like this, there is a unique commutative triangle which restricts those top two to be those. In other words, any two arrows have a unique composite. So that being an isomorphism actually adds in the algebraic structure of composition. And this works more generally. So let's analyze this. How did I know to take this pullback? Right? Like I came up with it, right? I was like, this is going to work. But here's how. If I draw these two things here, right? I need my, what was I using? Pink? If I draw these two things here, I can fillet it into its elementary components. So let me draw all the elementaries. Remember, an elementary is listed here. It was a free choice, but they're the ones that aren't built out of any other things. Here are all the elementaries, right? They each include these are all my elementaries and their inclusions, and they fit into each other. And these triangles commute in delta, right? So this diagram here that diagram, that's the diagram that I take the pullback in here. As you can see, I'm mapping into cat, so I get a duality. So this cospan in here turns into a span. Sorry. This span turns into a cospan that I take the pullback of, right? And you might be wondering, what happened to these other edges? Well, as it turns out, the really fancy way to say this is that this diagram is initial in this thing, but they don't affect the resulting pullback. The resulting pullback would say, and I have two other, technically, I have three objects, two maps, and this equation. But if I just write down the maps, they already come with their other objects, so I don't have to say that. Okay. So the Segal condition really is this: NC of some diagram D goes to the limit over all inerts from elementaries into NCE for the elementary. And Segal's theorem, so theorem the nerve is fully faithful, and its essential image consists of those Presheaves satisfying the Segal condition. He didn't say it like that. We say it like that. All right. So why does that work? I could spend the next 15 minutes explaining why that actually works and where associativity comes from. Hint, it comes from applying it to the three-length composite, looking at all the different ways you can factor it and being like, wow. But instead, I'm gonna do what I call double patterns, and I'm going to go on to talk about more things in that yeah.
Is double pattern 2C or 2B sub B?
2C, no. A double pattern is just it's just my own homebrew way of doing algebraic patterns that I like. So the question is this now. Okay, great. We have a notion of category coming from an algebraic pattern. As I've mentioned to you, there are algebraic patterns for other things like multi-categories and props and symmetric monodal categories, although asterisk on all those, on all the ones with symmetries, ask me about it. Actually, one nice thing is that the fact that the algebraic patterns don't have to come from familial monads means you can get better, some things become familial when you go into higher category theory, but you can do them in lower category theory, they just aren't familial. And it turns out to give you a little more, if you know what that means, whatever. Thank you, David, for nodding. Okay, I'll define now here. I can say it here before I go on, def. A model of an alg pattern P is a Presheave such that the Segal condition is ISO. So the reason Segal actually did this, just to say a little bit more before I jump and run really fast for the last 10 minutes. The reason Segal did this is, first of all, note that I can replace set by other things. For example, if I replace set by cat, and I still use my delta here, and I have the Segal condition, I end up with a category internal to categories, also known as a double category. I will note that the distinction between inert and active is a distinction which is very important throughout categorical algebra. And I'm going to say a statement that I don't expect anyone to totally grok, but I think I have to say it. It's in my notes. I just don't have space to write it on the board. But lax double functors, where do they come from if you see them, if you see double categories, strict double categories, as Segal objects for delta in cat? Well, they are lax natural transformations, which you can now have because you're landing in cat, but where the inerts are strict. And this is a general feature of categorical algebra, is that you often need to separate a composite, which could become lax or op-lax or pseudo or blah, 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 from a subdiagram, which should always map strictly. If you're looking at, for example, internal pseudo categories in cat as double categories and you want to look at double functors, you need to know that if you look at all the notions, on the two legs they have to be strict and on everything else they get to be whatever. That's because those two legs come from the inerts going into the box. And so that distinction between inert and active shows up all the way in two algebra. OK, anyway, here's our model. Now we're going to go and do double patterns. So the question we can have there, so maybe the theorem, you can read Segal's theorem over there as saying that the category of models for delta is cat. Right? The theorem right above this. We define a model to be a Presheaves satisfying the Segal condition, and the Segal theorem says that that is actually just cat again. So now we can use this to get, we sort of used cat to define our algebraic pattern, but now we can take an algebraic pattern and use it to define our categorical algebra. So the question I want to ask is, how can we take categories, form a virtual double category when equipped with profunctors and functors? And how can we do this when we're looking not at categories, but things like symmetric monodal categories, props, multi-categories, etc. So this will lead us to double categories, double patterns, and their models. So def, a double pattern is a double cat D, and then we write D naught. So we write like D, like we say D naught is also the vertical direction here, is the inerts. And D1 is the actives. D1, by the way, is the category of actives and these squares. So its objects are actives, and its morphisms are subcompositions. Another nice notion that we get. So this thing here is a subcomposition of this composition, okay? Which is actually a very useful notion. Okay, so that's that. Plus, there's one condition. So being a double pattern is just a double category plus one condition, or plus extra data, plus a subcat DL of D0, so some inerts called elementaries. And by the way, OK, and the target map T from D1 to D0 is a Cartesian fibration. Or also known as Grothendieck fibration. What does that mean? Well, that means that if I have an active whose target is the target of an inert, I can lift it to a square. And that's what this factorization is. So the theorem, algebraic patterns include into double patterns in the way I've just drawn them there. And this is why I joke that my big insight here is to actually draw the orthogonal things orthogonally. Here they're written in orthogonal directions. One's vertical and one's horizontal. I won't need that for my definition, so I'm just not going to put it in. This is, yeah, you don't need anything to do this. So now that we'll talk about a model. A model of a double pattern is a lax double functor d op, where that's op in the inert direction, m d op to span set. Plus conditions. The Segal condition. And the Segal condition. So now, where this is a active,
well, Segal condition is like a function from inerts, and it's also a function from actives.
So the Segal condition, this is the traditional Segal condition, in that this only actually has to refer to the inerts. Right? So this is a diagram of inerts. It's taking place in the category D0. Now I'm going to add a condition on actives. Again, it's a limit over elementaries of now the codomain of the active, which, by the way, is the domain in the algebraic pattern thing. I secretly flipped the direction of them. By the way, that's actually a nice thing, because one annoying thing about algebraic patterns is no matter which convention you choose, and by the way, mine's the opposite of Chu and Haugseng because I find those confusing, you mess up the intuition of one of the classes of morphisms. But if you use a double category, you can freely flip the direction of one without flipping the direction of the other, and you can have them both have the right thing. So my actions actually go in the direction that they compose, whereas theirs go backwards, right? Composition goes this direction. But in an algebraic pattern, the arrow goes that way. Small thing. Anyway, whatever. Here, I have this. Now I have this I, and it goes into D, and I have this alpha. It goes also into D. I'm ready to pop my condition, and I can lift this to M of lift over I of alpha. So what does that do? This is, in fact, functorial. Is that if I take more inerts in here, I actually get inerts over here that make the diagram sort of commute up here. Okay? Because this is a Cartesian fibration on these categories, right? So it uses the squares up here. Okay, so I will say this.
That's also an iso.
So yes, is iso. Thank you. If D comes from an alg pattern, this is a weak Segal fibration. If you read the paper, there's a definition of weak Segal fibration, and it has two conditions which make sense, and one condition which is confusing that involves the active, and that's the second one. I think it's clearer in the double categorical one. Now let's see if we can explain why these things are, in fact, a model of delta is a virtual double category. And then I'll say how we can use this idea to get the virtual triple category of double categories. Okay, so e.g. D equals delta. By delta, I mean delta, but put into the active inert way like this. Okay, so what do we get? M from delta to span set. Well, in the inert direction, right, we're going to send any list of these things to a set. But the first Segal condition is actually going to kick in, and we only have to say what it really does on the elementaries. So we have a set M line of objects because it's delta is a category, and I mean the double category that's built out of inerts and actives in this particular way. I just, without giving it a name, that's the best I could do. And this is going to be of loose arrows. Okay, we have sets like this, and then we have other things, right? So that the rest of them are given by the Segal condition from this. And then we have something like this. For a composition pattern, something like, let me do this smaller one up there, like this one, we get M of this 3 things, M of these 2 things, and then here we have a span, right? So I'll take M of this composition pattern like this. So how do we interpret this? Well, we're going to see it. This actually can be broken apart, right? Because remember, my second Segal condition says that M of alpha, this is certainly an M of alpha, is given by a limit over the elementaries of here. So in fact, this thing breaks up into a limit over these 2 boxes. So let me just look at what one into a single box would be. I'll do it down here. I won't draw that limit condition out because I'm running out of time here. But let me just do binary composition here. So if I look at this box, the corresponding composition pattern here is this binary composite on the left, right? So that's the one that would come out of this. So this span, I'm going to interpret this as, here I have a loose. So I'm going to, I need another color for my internals, maroon, I guess. This is a loose, right? This here is a composable pair of looses by the Segal condition. And this here is going to be a set, I mean, these are sets. This here is going to be the set of squares of this form, of cells of this form. Now, if I didn't really give this a didn't really plan this composite out right in order for this to work. If we have multiple ones of these, for example, if I have a ternary one, which I wish I could grab this and move it over there because I put it on the wrong side. Let me just flip the direction of this. Just in the interest of actually getting this thing here. Let me take that one to be this, right? Now, the composite of these 2 actives here is that right? So I think, yeah, the composite of these 2 actives is in fact the single one here. Right? And the fact that this is lax means that into the, I'll just drop this, right? The fact that this is lax means that there's a map into this pullback. Sorry. Out of this pullback. There we go. What does that do? It says that here, now I have to, so here, this, by the second Segal condition, splits apart into actually 2, one for each. Again, I'm writing the backwards along the page because I messed up. But this is one over here and one over here. So this is a, for this thing, right, it's a pair. This is a pair of things like this and a cell like this over the first one. And then over the second one is actually unary. Right? So by the Segal condition, it's actually the set there. And this one now is like this. And this one's a single one. Right? And this one's here is ternary. Right? Okay. And now, if I take these and these, I need to get something in here, which is a set with a single ternary thing on top and one thing on the bottom.
what do I do? Well, this map is given by this composite. Which you'll recognize from virtual double categories. And so that is how this assembles into virtual double categories. Thanks, that's my talk. Thanks.